This is a physics example problem called Rotating the Demo of Doom. Here's the problem we're going to be looking at. The Demo of Doom is a classroom demonstration apparatus. The demo has a lightweight bar with two 1 kilogram blocks attached to the bar. An axle through the midpoint connects a very lightweight disc, which has a radius of 7.5 centimeters, which has a light string wrapped around it. When the 2 kilogram mass is connected to the string and allowed to fall, the string pulls on the disc and the disc and bar rotate together. If one of the movable 1 kilogram blocks is 30 centimeters away from the axle and the other one is 50 centimeters away from the axle, what acceleration should the 2 kilogram mass have as it falls to the floor? So a couple of the important points to pull out of this is that the disc is described as being very lightweight. So this is kind of, at this level, physics code for we're going to ignore its contribution to the motion. The radius does matter, though. The radius of the disc being 7.5 centimeters. The masses also matter. So this 2 kilogram mass, it's important to understand what that is. The 2 kilogram mass in the problem is the one that's hanging right here. There are two 1 kilogram masses. Those are on the bar. So we have 1 kilogram mass that's 30 centimeters away and one that's 50 centimeters away. The final thing in here that I think is key is that as that disc turns, it turns the bar as well. And so what it says in here is that the string pulls on the disc and the disc and bar rotate together. It's important to have a good mental picture of what's going on there. So we're going to start by considering the cause of torque. What makes this whole thing rotate to begin with? Well, it's the 2 kilogram mass pulling down on the string. So this is a free body diagram of that 2 kilogram mass. So what I see here is that the force is acting. If I make a list of forces, they're all acting in the y direction. So we have tension that's pulling up. It has a positive sign. And we have weight, which is equal to mass times the acceleration of gravity, and that's going to have a negative sign. Now when we add these up, we find the net force, and that's going to be tension minus mass times gravitational acceleration, and that's also equal to the mass times the acceleration. So I can go ahead and put some numbers in here. I'm going to have 2 kilograms times the acceleration of the 2 kilogram mass, so I'll put a little subscript 2 just to give it a name. This is going to equal the tension in the string minus 2 kilograms times 9.8 meters per second squared. That's 19.6 newtons. I can rearrange this to solve for the tension. The tension in this case is going to be the 2 kilograms times the acceleration of the 2 kilogram mass plus 19.6 newtons. So we found the tension in the string, and the whole point of that was that I know the tension pulls right here on this string, and that produces a torque that makes this whole demonstration move. So let's consider the equation for the cause of torque. Torque is caused when a force acts at an r distance from the center of rotation, and then we take the sine of the angle between those two, the force and the radius, to calculate the magnitude of the torque. Well, in this problem, the force is the tension, the radius is simply the radius of this disc, and the angle between the force and the radius, that's 90 degrees. So some things are going to simplify here. So the torque is going to be the tension times that radius. If we look back at the problem, that was 7.5 centimeters, but we usually want things to be in SI units, so we need to convert that into meters. There's 100 centimeters per meter, so we divide 7.5 by 100, and that will give us 0.075 meters. And then multiply this by sine of 90 degrees. This sine of 90 degrees, well, that's just 1, so that's going to simplify things a bit. So now we have that the torque is equal to, let's put the tension in there. The tension is 2 kilograms times the acceleration of the 2 kilogram mass plus 19.6 newtons, and then all that is going to be multiplied by the 0.075 meters. So let's just distribute this. So now we've found that the torque, due to the things that are producing the torque, is going to be equal to 0.15 kilogram meters times the acceleration of that hanging 2 kilogram mass plus 1.47 Newton meters. So we've developed this equation that describes torque in terms of the cause of torque, the tension on the string. Now it's time to look at the effect of torque. So our general equation for the effect produced by torque is that torque produces an angular acceleration multiplied by I, which is the moment of inertia. The moment of inertia has kind of an intimidating name. Really, it just means the resistance that an object has to being rotated. Now, to calculate moment of inertia, if we were talking about a solid object, just a single massive disc or hoop, square, bar, anything like that, then we could either look up an equation to describe the moment of inertia, or if we were in calculus, it could be a good calculus exercise to perform an integral to compute that moment of inertia. In this case, we don't actually have a solid object. We have a system of objects. And the bar and the disc were described as lightweight, or even very lightweight, which remember is introductory physics code for we're just going to leave it out of something. We're going to leave it out of the moment of inertia. So the only things that we're really interested in being rotated are these two 1 kilogram masses. You might be wondering, what about the 2 kilogram mass? That's really important in this problem, but it's not rotating, it's simply falling down. So it is also left out of the moment of inertia. So to calculate the moment of inertia of a system of masses, we calculate the sum of each mass multiplied by its distance from the center of rotation squared. So to calculate this moment of inertia, we have a 1 kilogram mass located at 30 centimeters, which is 0.3 meters, and we need to square that from the center of rotation. Add to it the other mass in the system, also 1 kilograms, but this one is 0.5 meters from the center of rotation, and we need to square that. When we compute this out, the total moment of inertia of this system is 0.34 kilograms times meters squared. So we can go ahead and rewrite the torque as being equal to that moment of inertia times the angular acceleration. Now, something that's worth taking a moment to think about, the tension is being applied over on the right-hand side of this apparatus, which is going to produce a rotation in the clockwise direction. In rotational mechanics, we define clockwise rotation to be negative. And so this torque, the effect of it, is actually a negative 0.34 kilograms times meters squared multiplied by the angular acceleration. So what was the point of this problem again? Sometimes when you've been working on a long problem, you can lose track of what you were trying to figure out. We were trying to figure out this acceleration of the hanging mass. This new equation that we're developing, it has an alpha in it, but I don't see the acceleration in it at all. Well, remember there's a relationship between the angular acceleration and the acceleration of the hanging mass. As this demonstration rotates, it's unspooling a length of string, and that's allowing the 2 kilogram mass to fall. This means that there's a relationship between the angular acceleration and the falling acceleration in terms of tangential acceleration along this disk. So what that looks like in terms of an equation is the tangential acceleration around the disk is alpha times the radius of the disk. This is going to be equal to the acceleration of the hanging mass. As far as the plus and minus signs go, if this acceleration of the hanging mass is downward or negative, then this alpha is negative as well, since this is hanging off of the right side of the disk instead of the left side. We don't want to cancel acceleration out of our problem. That's what we're trying to solve for. And so I'm just going to do one quick algebra adjustment. I'm going to solve this for alpha. We're going to replace alpha with acceleration of the hanging mass divided by the radius. You might be confused about what the radius is. The radius here again, we're calculating tangential acceleration along this disk, so it is simply the radius of the disk, which was 7.5 centimeters or 0.075 meters. So now we're going to plug this in. So for our torque, the effect of torque is 0.34 kilograms times meters squared. Should be a negative sign out here. And we're going to multiply that by the acceleration of the falling mass divided by 0.075 meters. These torques, I have two equations for torque. They are the same torque. Remember, one describes the cause of that torque and one describes the effect of that torque, and so we can set those equal to each other. And now I can do just a little bit of algebra cleanup over here on the left-hand side, and I'm going to end up with a negative 4.53 kilogram meters multiplying the acceleration of the hanging mass, and that's going to be equal to 0.15 kilogram meters, also times the acceleration of the hanging mass, and we have to add to that 1.47 Newton meters. Alright, still with me? We're almost done here. Here's the equation we've come up with. The only unknown in it is the acceleration of the hanging mass. That's what we're trying to solve for. So now we're just going to do some algebra. I am going to subtract 0.15 kilogram meters times the acceleration of the hanging mass from both sides. And so that's going to leave me with a negative 4.683 kilogram meters times the acceleration I'm looking for. All that's equal to 1.47 Newton meters. So now I'm just going to divide both sides by the negative 4.683, and I will have my acceleration. The acceleration is a negative, or downwards, 0.31 meters per second squared. And that's my final answer.